This is a short video to discuss coefficient of determination. In the last video, we found our regression equation. The question we then have to ask is, how useful is our regression equation for actually making predictions? Remember, we're going to take this sample data. We're going to develop a regression equation from our sample data. And then we need to know, well, how useful will that equation be to make other predictions? We were looking at test scores. So how useful will that equation be to say, hey, if I study 8 hours, can I predict what my grade on the test is going to be? So this usefulness comes in a lot of there's a lot of ways that we can determine how useful a regression equation is. One of them is called the coefficient of determination. And the coefficient determination basically just determines the percent of variation in our observed values, so our test scores, that can actually be explained by the predictor variable, which in the problem we've been working on is the number of hours study. So keep in mind, this will be a percent. Your final answer for your coefficient of determination is going to be a value between 0 and 1. If you're not getting a value between 0 and 1, you're making mistakes somewhere. Our coefficient of determination is represented by r squared. We're going to introduce two new variables, two new terms, and that is the regression sum of squares, the total sum of squares, and we're going to introduce another one called the error sum of squares. And you're familiar with sum of squares from when we worked on ANOVA tables. So basically, let's take a look at a very simple, this has nothing to do with the problem we've been working on. This is just a very simple regression. We have we have 5 observed values. I just picked one of them out. I picked this one right here. It's some value x sub I, that's our observed x. Some value y sub I, that's the response variable, that's our some observed y. Okay, so if we were doing the test, x would represent, number of hours studied, and y would represent the test score for an individual. Okay, this is just one data value. So the first one I want to look at is this SSR. Okay, so we have a lot of different y's going on, and we talked about these different y's before. The y sub I is the actual observed value. And then for this x, there's another y. There's the y that lands directly on a regression line. That y is your y hat. So that y would come from the regression equation if I plugged in the x number of hours. That's the test grade. Notice there is a difference between y hat and y sub I. Now, there's another y we're going to talk about, and that is our I'm going to put it down here. I don't know exactly where it would fall, but this is our y bar. If I were to take all the y values and find their average, I would get y bar. So keep in mind for a second, if our regression equation, I'm going to draw just a little one real quick. We'll come back to this in a second. Let's suppose we had a regression equation that really showed no linear regression. If there's no linear regression, then our point estimate literally just becomes our mean. Okay? So that y bar represents, if there was no regression, here's where our points would average. Okay? Now, if we look at the difference between our y hat, whoops, I lost my equation there. Sorry about that. There we go. the difference between y hat and y bar, the average, is the variation in the observed values of the response variable that is actually explained by the regression equation. So if we didn't have any regression, our value would be on y bar, the mean. But since we have regression in this particular problem, this is kind of the deviation that is explained by the regression. Okay, and that's what our SSR is, our regression sum of squares. So that formula is taking the sum of each values y hat, subtracting the y bar, and squaring it. And that's where we get the regression sum of squares from. Now, if we look at the regression from our actual value down to our regression line, what we have here is variation that is not explained by the regression. Any deviation not explained by the regression. This could be sampling error, it could be a lot of different things. The closer our points are around our regression line, this would be much smaller. This one is simply any variation not explained by the regression. And we call that one the error sum of squares. So that one is the sum of taking each individual y, subtracting from the y hat you would get using your regression equation. Okay, now both of these together represent the total sum of squares, and that's the total variation in an observed value of our response variable. So that one, if you look at the picture, is going to be the summation of each individual observed y value minus the mean squared. This also leads us, and you can tell right from the picture, this is going to lead us to what we call our regression identity, which is simply states the total sum of squares is equal to the regression sum of squares plus the error sum of squares. That is your regression identity. Okay, so what we're going to do now is kind of use this idea, and these are our defining formulas. They actually define what's happening in our image above, but we have computing formulas that are going to make these calculations much easier. You're not going to have to go through, do all these differences, square them, and then sum them together. So let's go back to the data we were working on in the last video, where our predictor variable is the total study time over 2 weeks, and our response variable, our outcomes, is the test that you took after 2 weeks. We went ahead and in the last video, we calculated all our calculations, our S of XX, S of XY, S of YY, and we found our regression formula. So what I'd like to do, since we already have these calculated, let's look at our formulas for a second. Sorry, trying to erase everything on here. Okay. So here you can see our SSR, SSE, SST, and there right next to them are the defining formulas, but I would like to use these computing formulas. Since we already have these values, it's going to make it much easier to use. So recall, to find our coefficient of determination, which is r squared, we need to take SSR divided by SST. SSR computing formula is right here. Let's copy that onto our paper. So SSR is S of xy squared divided by, go back to your formula, you can see it, S of xy squared divided by S of xx. And our xy, so that's negative 133.5 squared divided by S of xx is 157.86. Go ahead and do that math and you should get 112.9. Go. So check for yourself, please. Now, remember, r squared is the regression sum of squares over the total sum of squares. Okay, what part of the total can actually be explained by the regression? That's the percent we're looking for. So go back to the formula. SST, if you kind of take a look down here, there is our computing formula, but SST itself is simply S of YY. So all we need to do is SST equals 188. We've already calculated that. So then we can find r squared to be the 112.90 divided by 188, and that will give us 0.60. We would write that as 60% of the variation in our observed test scores sorry, I'm trying to go fast here. Our observed test scores is explained by the number of hours studied. So sometimes you get these percents much closer to 1, much closer to 100%. That's when your points are very close to that regression line. If your points are more spread out from your regression line, you're going to get a lower percent. Okay, thank you.